G'day, Chris here and welcome back to ClickSpring. There's much commonality in how the various parts of the Antikythera mechanism have been made. When considering the machine as a whole, a given metalworking technique, for example using a file to form a feature or using peened rivets, is repeatedly used in much the same way across the device. These are the well-tested standard techniques used to solve the problems created by the various design requirements that outside the context of this machine might be considered fairly routine. But like most machines, there are critical components that have been made using processes that go beyond standard technique. These are the specialist, advanced operations that serve to show the level of finesse that existed in the ancient workshop. In this video, I'd like to show three that stand out to me as products of the lathe technology of the period that are essential to some of the machine's functions. There are many well-fitted bearing shafts in the device, each slightly different from the next, solving the problem of how to carry a given load in its own way. Most share the characteristic of being fairly robust, and so wouldn't have presented an unusually difficult challenge to make. But there's one that stands out as being quite different, and is an essential component of the lunar phase assembly. It's a shaft about 20mm long, a little over 1.5mm in diameter, with a squared driving boss at one end for a crown wheel. It carries the moon phase ball of the assembly at the other end and is constrained within a small pipe inside a rotating drum-shaped assembly. The shaft section must run quite true, and overall the part must meet a number of demanding dimensional limits. This arbor is a small fraction of the size of most of the others found in the mechanism, and although its fabrication likely started out much the same as the rest, it would have required a careful approach to complete it successfully. The challenge of this part will be entirely familiar to anyone who's used a modern lathe to turn a slender shaft. One of the main problems is that they become weaker as they approach their final form, and so tend to deflect and potentially jump up above the cutting tool, ruining the part. So both the cutting forces and the order of operations need to be carefully managed to have the largest cutting force brought to bear while the stock is rigid, and then have it gradually reduce as the workpiece becomes more vulnerable. The other challenge is in achieving a true cylindrical shape for the shaft section. One way to achieve this between centres is to carefully set the target diameter at each end, and then with much less risk of damaging the part, bring the rest of the section down with a file and stones. Now a file is a tedious way to remove metal on the lathe, and not generally the first choice for bulk metal removal. But aside from the more distributed load, it brings the added benefit of being reasonably flat to begin with, and so generates a surface that can be steered towards being cylindrical by eye without much difficulty. In its present state, the component is completely fragile, and certainly wouldn't be able to withstand deflection under even the gentlest lathe tool cutting force. But from here, it no longer matters, because the riskiest operation is complete, and the rest of the profile can be formed off the lathe using files and stones. Now, one thing worth mentioning about the gradual move towards limiting this Antikythera reproduction to the tools of the day has been the way the limitations have naturally revealed simpler solutions to various problems. It often becomes apparent when avoiding the option of modern tools that a requirement, like for example indexing, can be solved with no extra tools at all, just by building something simple into the process. In this case, a little basic forging of the driving end of the workpiece blank to create 4 reasonable starting surfaces to work with. It turns out that nothing more is needed to go from a fairly crude index source like this to something consistent with a standard that can be seen in the wreckage of the mechanism. The squared boss dimensions are slightly oversized at this point, with a slight taper to the smaller section, all in preparation for the later fitting of a crown wheel that I'll cover in a future video. Okay, so another essential part is at the heart of one of the most impressive features of the machine, the epicyclic pin and slot gearing that models the ancient Greek theory of the variable motion of the moon. I've covered this aspect of the mechanism in a previous video, so be sure to check that one out for all of the detail. But the thing to know for this video is that this entire feature quite literally revolves around this solid bearing component that has two parallel yet slightly offset axes. So how might this component have been formed in antiquity? Again, one solution rests on building in some fairly straightforward features into the workpiece blank. To begin with, the larger diameter of the part is formed, in much the same way as any of the larger shafts of the mechanism. To form the smaller diameter, the work must be shifted to an adjacent parallel axis. When forming the blank stock, I forged some rough flats at each end. The most presentable of these now serves as the starting point to generate a pair of fairly crude reference surfaces at each end of the workpiece. An offset can then be marked, and a suitable pair of offset pivot holes formed. The work is now returned to the lathe, but this time mounted on those newly formed pivot holes. Depending on how accurately they've been placed, the work is now rotating offset and parallel to the original axis. With careful management of the initial interrupted cut, this then becomes a practical method for the controlled formation of a feature eccentric to the first diameter. Again, although a little slower, switching to the file and stones for the finishing cuts makes it much easier to generate a cylindrical feature. The great benefit of between centres turning is that the workpiece can be repeatedly removed and then returned to the lathe, in this case even changing axes, for repeated operations as required. As before, the features formed into the raw stock help with the indexing of the boss section. And again, the boss section has a slightly tapered lead and extra overall length to assist during fitting, with the functioning diameters, heights and offsets able to be set at the whim of the maker as per the requirements of the mechanism. Now, aside from the many quite shallow bearing, register and fastener holes within the mechanism, there are several relatively long bearing holes of small diameter. A good example is the hole required to receive the shaft made earlier in this video. I've covered the technique required to form a simple spade drill cutting edge previously. It's known to be one of the oldest drill bit forms and performs well for what it is. But what about the drill stock itself? That also needed to be well formed and true to generate these high standard holes. Again, a perfect role for the lathe. Once worked into the basic shape, the soft iron must be transformed into something capable of holding a cutting edge. After the quench, the bit is glass hard and so must be tempered, a process that transforms the material from brittle into something tougher suitable for cutting. From there, the cutting edge can be raised on a brace of stones. Even today, long thin holes present a challenge, especially if the hole is to act as a bearing. The slightest interference will affect performance, and in the case of a low torque gear train, is likely to cause binding. So it's tempting to imagine a circumstance where some sort of rest or attachment to the lathe could have been used to assist in helping to use this drill bit, even if only for those holes that needed to be drilled true to an already existing feature, or perhaps to make a repair or modification to an already turned part. I've lightly forged a small attachment for the bow lathe, using a punch to form a cone indent, and then drilled and filed out the end to permit drill bit access. In this hypothetical arrangement, the workpiece is well supported, and it's straightforward to present the bit to the work in a controlled way. The bit certainly cuts well, and overall, things can be managed for the hole to proceed to full depth. This approach is not overly time consuming, and it delivers a reasonable quality clearance hole. But it's also easy to imagine an experienced turner in antiquity simply doing away with even this add-on, for the sake of the speed and convenience of entirely freehand drilling. Because remarkably, for a bow lathe, it's enough to simply use the point of the drill bit as one of the pivot points, and then get to work. The rotational action establishes the start of the hole, and with a little care, once it gets beyond the initial cutting edge, the cylindrical body of the drill bit tends to assist in keeping it on course. Now, the standard spade bit does a great job of stock removal, but should the maker have decided that a reamed, more precisely sized hole was required, this initial hole could be followed with a simple reamer. We have historical examples of reaming tools that I've shown in a previous video. One of the simplest and most effective, widely used today, is the 3-facet reamer. It's as easy to form and heat treat as the spade drill, and outstanding for generating a well-sized and finished hole. The short turned section that I cut into the end of the workpiece tends to help keep things stable for the first few turns of both the drill and reamer if the exterior surface of the stock is otherwise coarse. But after the first few careful strokes of the bow, the cutter again neatly self-guides to the full depth of the existing hole. The workpiece can now have its perimeter filed relative to the axis defined by this hole, as required for whatever the part needs to be. For example, as the pipe that accepts the shaft made at the start of this video. The device that we call the Antikythera Mechanism was an ambitious effort for its time, a confident expression of the ancient workshop tradition of working metal into delicate and useful forms. These essential operations were an expression of that confidence at the part level, a demonstration of mastery that continues to resonate even after 2,000 years. Thanks for watching. I'll see you later.